In this video, I will explain the modeling and MATLAB simulation spring damper system. This video is divided into 6 parts, namely main content, schematic diagram of the system structure, derivation of the time domain model, and the transfer function in the Laplace domain. The first is MATLAB modeling, and then is analysis of simulation results, and the final is summary and demonstration. This is the part 1 main content. My homework is one is create the time domain model, then Laplace model to create the transfer function. The second is create the MATLAB model, then show the plan for setting time and system response. This is the part 2. First, let's look at the schematic diagram of the system structure. As we can see from the figure on the left side, is damper, labeled as damper B, which is connected to the wall. On the right side is a node, and the external force Ft acts on this node. At the same time, the node is also connected to the mass m. Based on this structure, let's analyze its mechanical relationships according to the principle and mechanical equilibrium. The external force Ft is equal to the sum of damper force F, and the internal force Fz, that is Ft is Fe plus F1 plus F2. Among them, the calculation formula for the damping force F1 is Fx is Bxt, and the damping coefficient and Fxt is velocity. The calculation formula for the interface force F2 is F2 mxt, where m is mass and the xt is the acceleration. Those two forces together maintain with the external force and are important base for the subsequent model building. After understanding this system structure and mechanical relationships, we can travel the time domain model based on Newton's second law. Newton's second law tells us Newton's second law tells us that the acceleration of an object is directly proportional to the net force action on it and inversely proportional to the mass of the object. Combining with the mechanical relationship, Ft is F1 plus F2, obtained from the previous page, substituting the damping force F1 is B dot xt, and the internal force F2 is m xt. Into it we can get the time domain model of the system. Having obtained the time domain model, the next step is transform it into the Laplace domain to get the transfer function. After zero initial conditions, take the Laplace transform of both sides of the time domain model. The mxt plus bxt is ft. According to the properties of the Laplace transform, the Laplace transform of xt gives bxt gives sx. The Laplace transform of f dxt gives xs, and the Laplace transform of ft gives fs. After substitution, we can get 1 second as 0.1 second as plus 5s xs is fs. Then we rearrange this equation, separating the radio of fs xs to fs. Thus, we obtain the transfer function of a system is xs fs is 1 and 1000 s plus 550 s, and the final is this. And this is the part for this code. This is the part for MATLAB modeling. In this code fully realizes the modeling and analysis of spring damper system from parameter defining model construction to response coloration, cover plotting, and performance analysis. It clearly demonstrates the domatic characteristics of the system under action of a step force, providing intuitive resource for understanding the system behavior. Next, I will analyze to periphery of periphery. This section of code demands the core physical parameters of the spring chamber system. The mass m damping the B and external force F are foundation for constructing the system model. They directly correspond to characteristics of the actual physical system, providing data support for subsequent modeling. Based on the parameters, the transfer function of a system is constructed. The numerator and the NUM and the DEN corresponds to formulas divided theoretically, and the TF function converts them into a system model SYS that can be recognized by MATLAB, which is the key to connect several and simulation. Set the simulation time range and calculate the response. T defines the time x from 0 to 200 seconds. The step function calculates the displacement response under a 500 step force, obtaining the displacement y and the corresponding time t out. Visualize the response data. The plot function is used to drive a curve of displacement changing with time. Labels and grids make the curve more reliable, visually presenting the thematic changes of the system. This is calculate and output the system performance. First, determine the stay theoretical steadily and stay value and adjusted the dimensions. The step if function analyzes the response to obtain the setting time. Finally, use for printf to print the resource, achieving the qualification of performance. This is the part 5 analysis of simulation resource. Now let's look at the simulation resource in MATLAB. First, consider the velotic response curve from the curve. We can see that the velocity shows a monotonically increasing trend. As time goes by, it finally separates at about 10 10 minutes 1 second, which is consistent with the steady state velocity. We obtain data from our analytical solution. Verifying the currentness of simulation results. Next, look at the displacement response curve. The displacement shows an approximately immediately increasing trend as time increase. That is to say, the displacement will continue to increase with time, and there is no stable limit value. This is the This is the demonstration of the final results. First is the code I used, and then I look at a lot of run and error to find and get it right. Next, click Run to obtain the simulation results. Okay, my explanation is over. Thank you for everyone.